So how exactly are proteins made? We are now going to go over the steps of translation. How do we go from an mRNA molecule to a polypeptide? So, like most of the things we've talked about, there's an initiation, an elongation, and then a termination phase in translation. So in initiation, we need to build up the machinery. So we have to be able to have the large and the small subunits engage with the mRNA and the tRNA, and that tRNA has to be charged, and all things have to work together to get this going. Okay? So, initiation. And we're going to talk bacteria and eukaryotes because we know from experience that these things have some differences in them. So in our bacteria, our small subunit has initiation factors 1 and 3 bound to it. Okay? And then the mRNA is going to interact with it. So the mRNA binds to it, and we are scanning looking for the Shine-Dalgarno sequence because the Shine-Dalgarno sequence contains the start codon. Well, it shows you where it is. So here's the cell Shine-Dalgarno, and here's our start sequence. And you'll see that the Shine-Dalgarno sequence is complementary to the 16S RNA. So here's our 16S RNA on our ribosome, interacts with this Shine-Dalgarno, which is positioning the start codon into the P site. The initiator tRNA molecule is the only one that starts in the P site. So we have our small subunit, the initiation factors, and now our mRNA molecule in its correct position. Then we have initiation factor 2 that brings our initiator tRNA with it, and this is a formylmethionine. It's a modified methionine attached, and this is how we do our start codon in bacteria. Once this comes, our initiation factors are released. They have to be released in order for the large subunit to bind. Okay, so when they are hanging out here, they are stopping the large subunit from binding prematurely. Now, once they come in, this solidifies this initiator into the P, and now we are done initiation in bacteria. In eukaryotes, it's kind of similar, but they don't have a Shine-Dalgarno. So here, they have eukaryotic initiation factors, so there'll be an EIF here. You have the initiation factors that are associated with your small subunit, and this is usually EIF2. So eukaryotic initiation factor 2, you can't. Okay, so let's just talk about it since we can hardly see it. So initiation factor, or EIF2, binds to the tRNA and brings it to the small subunit. We don't have a Shine-Dalgarno. Instead, we have a codec sequence that contains our start site. And so initiation factors help the initiator tRNA to bind to the subunit. We are going to recognize the cap. Remember, one purpose of the cap was to help initiate translation. So we're going to recognize the cap, and then we're going to scan along looking for the Kozak. Where the Kozak is where our start sequence is. Once we find that, we hang out there, chilling, waiting for the large subunit to come on. When the large subunit comes on, again, it perfectly places the initiator tRNA in the P site. Here's our codec sequence, okay? And you see that AUG is usually contained within that codec sequence. Elongation. The same thing happening over and over again after we get to stop. So what happens? So we have initiated. Now we are waiting for the next amino acid, for the next amino acid bound to tRNA to come into the A site. So the tRNA that has the anticodon to the codon comes into the A site. While it's there, we're going to form a peptide bond between the amino acids. So we form the peptide bond. This is peptidotransferase, remember. So now we have these amino acids bound to our first tRNA. Our second tRNA, or the tRNA in the P site, is now uncharged. There's going to be a shift Once we shift, we put what was in the A into the P and what was in P into E. This E has this uncharged tRNA that can leave. The one in the P site is going to stay there and wait for the next amino acid to come in so that we can keep doing the same process. Amino acid comes in, peptide bond is formed, shift, one leaves, wait for the next one to come in, and we do this over and over again until we get to a stop codon. So the tRNA is in the cytoplasm, enters the A site, moves to the P site, E site, goes back to the cytoplasm, comes in charged, leaves uncharged. Okay, so charged tRNA with its amino acid comes into the A site, peptide bond is formed, translocates to the next one, peptide bond stays, the uncharged goes into the E and leaves. Now for termination. So we have grown. Now we have reached a stop codon. Once we reach the stop codon, we're waiting still for whatever's coming in to come in. Now it's not going to be a tRNA that comes in. Instead, it's a release factor. So release factor 1 or release factor 2. Release factor comes into the A site. Once release factor comes into the A site, it causes everything to dissociate. So we get this RF1 or T2 that comes in. The tRNA leaves uncharged. The polypeptide is free to be able to be converted into protein, so to get folded. The mRNA dissociates. The 5S and the 30S comes apart, and they'll probably be bound with initiation factors to keep them apart. And we can do this process over and over again. Okay, so initiation, we have initiation factors. We have the small subunit that interacts with the tRNA and the mRNA, and then the large comes on. Then we keep coming in, finding complementary tRNAs until over and over again to build our amino acid sequence or polypeptide. We encounter a stop codon, release factor comes in, everything dissociates. These things can be recycled.